You are most welcome to the first episode in the study of electrostatics for advanced level physics. I am Bright Okwesiga Amoth. Credit goes to Mr. Onyait Justin Edmond for the notes that we are using throughout these episodes of electrostatics. In this episode specifically, we are looking at introduction to electrostatics. Now, what is electrostatics? The word electrostatics can be broken into two. One, we have the first part is electro, and the other one is statics. Now, electro refers to electrons, comes from the word electrons, and therefore that is due to is charge, because electrons are the charge carriers that we know. Then statics is a study of, when something is static, then it's not in motion. So the study of something which is not moving is what we call statics. So electrostatics is the study of electric charges at rest or that are not moving. What do we study about these charges that are not moving? These charges, they always generate forces between them. If you have any two charges, or three, whatever, but between any two charges, you'll always be having a force either of attraction or repulsion. And there is an area around this charge where that force is experienced, which we call the electric field. So we'll be looking at these electric charges at rest. We study about the forces between them, and we study how these forces affect the area or the regions around them. Those are electric fields. This electricity, which is static or which does not move, occurs when positive and negative charges collect on the surface of objects. There are several methods in which we can cause these charges to collect on the surfaces of objects or on the surface of any object. One of them is by rubbing certain materials against one another. Another way is by bringing a charged material near a neutral material. Then the other way is by sharing the charge on one body or on one material with another neutral body by bringing them into contact. You can simply rub them together, you get charge. You can simply bring an uncharged body near a charged one, and then a charge will be induced on the neutral body due to the charge on the charged body, that is charging by induction. Or we can simply share the charge. We redistribute the charge which was only on one body, and it is shared between two bodies. Let's begin with electrification by friction, or charging by friction, or by rubbing. When two bodies which are not similar are rubbed together, they generate heat between them. If you get your pen and you rub it vigorously against your hair, when you bring that pen near your skin, you feel that it is somehow warm, so heat has been generated. Even when you rub similar bodies like your palms, when you rub them together for some time, these hands become warm. Now, that warmth is due to the heat generated. Now, I would like to talk about something called work function. Materials have electrons which are a part of their atomic structure. They are part of the atoms. But these electrons are firmly bound to their nuclei by, by electrostatic forces between the electrons and the nucleus. However, as it is for any other force, we can overcome any other force by doing work against the force. In other words, we can succeed in pulling away or causing an electron to leave the surface of a conductor or the surface of any other material, even if it's not a conductor. Now, the energy that we are required to use to liberate or to remove one electron from the surface of any substance is what we call the work function. So work function is the minimum energy that we require to remove one electron from the surface of the material. Now, different surfaces of different kinds have different work functions. Some have a big work function, others have a small work function, which means the one which have a low work function can easily lose the electrons. The ones which have a higher work function require so much energy to release the electrons from their surfaces. When we rub two bodies together, heat is generated. Now, if this heat energy is taken up by the electrons, this amount of heat energy can either be less than, equal to, or greater than the work function that we have talked about. Now, when we rub two materials together, one is having a low work function, the other one is having a high work function. That means the one which has a low work function will easily lose electrons because it requires a small energy to allow the electrons to go away. So when the work function is less, that material will release electrons and they will be gained by the substance or the material with a higher work function. The one that receives electrons, it means it will now have an excess of negative charge. Therefore, it becomes negatively charged. The one that will have lost electrons or the one which has a low work function will now remain with an excess positive charge, and therefore it becomes positively charged. For example, when you rub a polythene rod, also called an ebonite rod, when you rub it with the fur or the woolen duster, the polythene rod becomes negatively charged while the duster becomes positively charged. That means the polythene rod has gained electrons because it has become negatively charged. The one which has become positively charged, which is the woolen duster, for it has lost the electrons. That means when you rub duster and woolen duster and polythene against one another, the polythene rod has got a higher work function than the woolen duster. Therefore, the duster will lose electrons to the polythene rod. Another example is if a glass rod or what we call cellulose acetate is rubbed with silk. The glass rod has got a lower work function than the silk. Because the glass rod has a low work function, it will lose or donate electrons to the silk. So the silk therefore becomes negatively charged, while the glass rod becomes positively charged. Insulators, semiconductors, and conductors. A conductor is a material which has freely moving electrons within its body, and it can allow electricity and heat to pass through it. In other words, it has free charge carriers. We said electrons are the ones that carry charge. So a conductor has got free electrons that are able to move across it and therefore carry charge or carry heat with it. Examples of conductors include copper, bronze, and others. An insulator is a material which does not have those free electrons which roam around carrying charge and heat, and it can therefore not allow electricity or heat to pass through it. Examples include dry wood, plastics, concrete, stones, and all that. Those ones don't allow heat or electricity to pass through. But specifically here, we're interested in the flow of electricity. Semiconductors. Semiconductors allow electric charges to pass through them, but minimally or but with difficulty. And these ones always break down and conduct current or allow charges to pass through them at very high temperatures. You need to heat them seriously for them to allow current to pass through them or charge to flow through them. Those are semiconductors. Examples include moist paper, moist air, paper, and others. The law of electrostatics. This law states that like charges repel each other, while unlike charges attract each other. If you bring here a positive charge near another positive charge, they will be pushed away from one another. They try not to meet, so they are repelling. If you bring a negative charge near a negative charge, they repel because they are like charges. But if you bring a positive charge near a negative charge, they will attract one another. And therefore, the law shows us clearly that like charges repel, whereas unlike charges attract. We need to take some precautions when carrying out experiments in electrostatics. One of them is that the apparatus must be insulated, because when we just touch a conductor, our bodies themselves can conduct away the charge on them. Or even when you place them on the ground without an insulator, the ground can easily conduct away the charge. And therefore, we need to use that. Then the surrounding air must be free from dust and moisture, because these ones aid the leakage of charge from the surface of materials. We shall be looking more so at charge leakage when we reach the point of corona discharge later. Now, much as we have said that like charges repel and unlike charges attract, a neutral body can be attracted by a charged body. A neutral body can be attracted by a charged body. I would like to explain why a neutral body can be attracted by a charged body. Consider a neutral body here. This neutral body, it means it has got an equal number of positive and negative charges evenly distributed across it. So for it has got, when a body is neutral, it means it has equal positive and negative charges. When you bring a charged body close to it, let me bring now a positive charged body. These charges on this neutral body will now redistribute themselves. The negatives will be attracted to the end near the positive charges, whereas the positive ones will be repelled to the far end. Now, these ones, the positive and the negatives here, are close to one another. So they experience a big force of attraction. Because they're close to one another, so they attract themselves strongly. Then, the ones which are far, the positive charges, they are repelling the far positive charges. So the force which is repelling this one is a weak repulsive force. Why? Because of the distance between the unlike charges. So in the end, since the body is experiencing a stronger attraction force compared to the weaker repulsive force, in the end, our body will receive a net attraction force, because the attraction force here is bigger than the repulsive force. Now here I have used a positively charged body near a neutral body. You can as well read through this paragraph and you'll see what happens when a negatively charged body is brought near a neutral body or conductor. There is a very common instrument we use in electrostatics and is called the gold leaf electroscope. Let us remind ourselves of the gold leaf electroscope. The gold leaf electroscope has got a very simple structure. It has got a brass cap. Now this brass cap is connected to a brass rod. Remember, these are all conductors. That is the brass rod. On this brass rod is attached a gold leaf. The gold leaf is also a conductor. Then the whole setup is enclosed in a metal case, but because the metal conducts, we have placed an insulator between the brass rod and the metallic case. That one is the insulator there. Now, our experiments with the gold leaf electroscope will mainly depend on the behavior of the gold leaf. So we leave here a window, a glass window, to allow us to observe what is happening between the gold leaf and the brass rod. All these ones, in most cases, though they didn't show it in these notes, is placed on an insulator to avoid the charges flowing or running to the earth in case it is placed in the ground. Then, to avoid the metal case from affecting the divergence of the gold leaf, the metal case is Earth so that it is kept at zero potential. What is the use of this gold leaf electroscope in experiments? One, we can use the GLE or gold leaf electroscope to test for the presence of charge, to know whether a body is charged or not. Two, to test for the sign of the charge. Is it a positive charge or a negative charge? Three, to test the magnitude of charge, to know how big the charge is on a body, the quantity of charge on a body. We can use the gold leaf electroscope to measure potential difference, PD. We shall look at each of these ones in detail. Electrostatic induction. Now, induction is to cause something to happen without there being direct contact between the cause of that action and the body that is experiencing the action or carrying out the action. I always like using examples that there are things which happen whereby, for example, if you look at someone who is cleaning the blackboard and he has no duster, so he decides to use a piece of dry paper to clean. Sometimes as he cleans, you feel as if something is happening to your teeth. The teeth become like so sensitive as if it is running against your teeth. So they haven't touched your teeth, but the induction, that action on the blackboard is inducing a feeling on your teeth. Or when someone is biting a sweater, these sweaters which have threads, you feel as if your teeth are about to burst, crack. That effect is due to induction. So induction, the same thing happens in charges. That induction, by induction, we want to create charge on a body, or we want to charge a body by simply bringing a charged body near it, not necessarily bringing a body to touch it, but just bringing a charged body near it. A body is neutral, but you bring another body which is charged just near it, and this body which is uncharged becomes charged. That is charging by induction. Now, the general principle shall be following when dealing with charging by induction. The body that we are charging will always acquire a charge which is opposite to the charge that is being used in the induction. If you bring a negative charged body near a neutral body, the neutral body is most likely to attain a positive charge. That is a charge which is different from the charge which is brought near it. Charging a gold leaf electroscope by induction. Charging a gold leaf electroscope by induction. We want part A to charge the gold leaf electroscope negatively. Now, remember, if we want to charge the body negatively, we use a positive charged body is brought near it. So step number 1, a positively charged glass rod, you can just say a positively charged body is brought near the cap of the gold leaf electroscope. Remember, our GLE is neutral. So when we bring a positively charged glass rod, what happens? Negative charges will be induced on the cap. Here is the cap of the gold leaf electroscope, and the positives will be repelled or pushed to the brass plate and to the gold leaf. Because the positive charges are collecting on the brass plate and the gold leaf, they will cause a repulsion. Therefore, you will see the gold leaf diverging. So there is a divergence here. Because the charge, let me try to make it a little bit wider for us to appreciate what I'm talking about. So when you bring the positively charged rod near a neutral gold leaf electroscope, this is the positive charged rod, the negative charges are all attracted to the brass cap of the gold leaf, whereas the positive ones are repelled to the brass plate and the gold leaf. Because of these charges around here, the brass plate will repel the gold leaf. So you'll see a divergence. Now, while we are still holding our positive rod in place, the gold leaf, the brass cap of the gold leaf electroscope is earthed. Please, here should be the brass cap. The brass cap of the gold leaf electroscope is earthed. But this one, you're doing it while you're still holding the positive charge in place. So when this is earthed, what happens is that the electrons which had gathered on the brass cap will not leave because they are being attracted by the positive charges. Instead, the electrons will come from the ground through the brass cap, then they will go and neutralize all the positive charge which was on the brass plate and the gold leaf. Now, this comes from one major and key observation, which is positive charges are massive and they don't move carrying charge. So for them, they are not charge carriers. It is electrons which are light that move freely, and these are what we call charge carriers. So much as the positives have been pushed down by the much as the positive charges had been pushed down the gold leaf, and the brass plate, this time they are not moving through the earthing to escape to the earth because they are massive and they are not charge carriers. Instead, the electrons are moving from the earth to come and neutralize those positive charges on the brass plate and the gold leaf. So we are now remaining with only the negative charges on the brass cap and the positive charges on the inducing rod. So before you take away the inducing charge, you remove the earthing. When the earthing is removed, while still holding our inducing rod in place, because if you do it after taking it away, these electrons will run out to the earth. So you keep it there while you remove the earthing so that you remain with your negative charge on the brass cap, because our aim was to charge the gold leaf electroscope negatively by induction. After doing that, after removing the earthing wire, the glass rod or the inducing charge is later on also removed. After it has been removed, the electrons which are on the brass cap will redistribute themselves on the brass cap, on the plate, on the gold leaf, and will cause again the gold leaf to diverge. Therefore, we have charged our gold leaf electroscope negatively by induction. What about charging a gold leaf positively by induction? Remember, if you want to charge a gold leaf electroscope positively, then you're supposed to use a negatively charged rod. As the rule was saying for induction, the body that the type of charge that you use to induce or that you bring near a neutral body will cause an opposite charge to be attained by the body you're trying to charge. Now, since we want to charge the gold leaf electroscope positively by induction, we shall use a negatively charged rod. It is brought near the cap of the gold leaf electroscope. It will induce all the positive charges which were on that electroscope on the brass cap and will repel the negative charges to the brass plate and the gold leaf. In so doing, the gold leaf is pushed away from the brass plate because they are like charges and will diverge. So you'll see a divergence. Now, while we are still holding our inducing negative charge in place, we are going to earth the brass cap of the gold leaf electroscope. Please here there is a missing statement. The brass or the brass cap of the gold leaf electroscope is earthed. What happened this time? Remember, we had electrons which had been pushed to the brass plate and the gold leaf. They are looking for an escape route because they are trying to run away from the negatives which are on the inducing rod. So when you attach the earthing, these electrons run to the earth through the earthing. Take away the earthing wire while you are still holding the inducing charge in place. This is key. Never take away the inducing charge before you have taken away the earthing, because if you do so, electrons which had run to the earth will run back to neutralize the positive charge which is on the brass cap. So after taking away the earthing wire, we can later on take away the charging rod. Therefore, the positive charges will now redistribute themselves on the brass cap, brass rod, brass plate, and gold leaf, and thus again causing a divergence. Thus, the electroscope is now positively charged. Testing the sign of charge on a body. Testing the sign of charge on a body. Now we want to know that any charged body, is it charged? Is it neutral? If it is charged, is it positive or negative? Now, if we want to test any the sign of a charge on any charged body, the first step we shall do is to charge an electroscope. Now, in this time, we are charging the electroscope negatively. When we charge it negatively, of course, as we saw, the gold leaf diverges. So after the gold leaf has diverged of the gold leaf electroscope, now we bring the body we want to test near the cap of the gold leaf electroscope. If the leaf diverges or increases further, then the body is also negatively charged. Get me well. If you have charged a gold leaf electroscope negatively, and you bring a body whose charge you want to test near the cap of the gold leaf electroscope, and you see divergence, then the charge that you see increased divergence, then the charge that you are testing is also negative. So negative charge on gold leaf electroscope, and you see an increased divergence, then what you are testing is negative also. Confirm negative. If the gold leaf electroscope is charged negatively at first, and you bring a body near the cap and you see increased divergence, then the charge you are testing is also positive. Now let's understand why this one happens. When the gold leaf electroscope is negatively charged, already it has caused a divergence. Already it has caused a divergence between the gold leaf and the brass plate because they have similar charge. Now, when you bring a negative body near the cup, even the negatives, remember the negatives had already been split across the whole deal. You on the brass cup, brass rod, brass plate, whatever. But if you bring another negative charge near the cup, even the ones which were near the cup, the negative charges which were near the cup will also be repelled away or pushed away. So we shall have a massive negative charge on the brass plate and the gold leaf. So the more the charge there, the more the repulsion. So you see more divergence of the gold leaf. So the divergence of the gold leaf implies that the body you are testing has the same charge as the charge you had given the gold leaf electroscope. However, if you bring a body which is charged near the cap of a charged gold leaf electroscope, and you see a decrease in the divergence, and you see the gold leaf somehow collapsing a bit. You can't say now that what I'm testing is different from the gold leaf electroscope. Here there are two outcomes. Either the charge you are testing is opposite to that of the gold leaf electroscope. I'll soon explain why. Or what you are testing is neutral. So when you see the leaf collapsing a bit or the divergence reducing, the test is inconclusive. You can't decide. You cannot decide. Why? If I bring a positive, if I bring a negative charge near the cap of a positive electroscope, the negative charge brought near the cap will attract more positives. Even some will come from the gold leaf and climb upwards. When they leave the gold leaf will have a lesser charge there, and the repulsive force will reduce, and we see a reduction in divergence. The same thing happens when we bring a positive body near a negative electroscope, or a negative body near a positive electroscope. What happens if we bring a neutral body? If I bring a neutral body, remember the other time we said the neutral body and an uncharged body can also attract a charged one. So the neutral body brought near the cap of the gold leaf electroscope will also attract the end in net attraction. So the charges will also reduce and hence cause a decrease in divergence. So if you see a decrease in divergence, then you cannot decide what you do. You discharge the gold leaf electroscope, charge it differently, and test the body again. If this time it diverges, then you conclude. If at again, if that the charge you that the body is charged and the opposite letter, now what you have similar to what you are now you have charged later. But if you bring it and after discharging and charging the gold leaf differently, and again you see the leaf decreasing in the divergence, then you are very sure that the body you are testing is neutral because or uncharged because it has caused a decrease in the divergence on two different occasions when the gold leaf has been charged differently. Charging a body by induction or charging a conductor by induction. Now here we have two cases. Case number one is charging a body positively by induction. Positively by induction. If you want to charge the body positively by induction, we use a negative charged rod. Now we bring the negative charged rod near the neutral metal sphere placed on an insulating stand. Why do we do so? To avoid charges which have been generated to run to the earth. When we bring it near a neutral conductor, the negative charges on the inducing rod will attract all the positives to the side near the inducing rod and will repel all the negatives to the far end of the metal sphere or the conductor. Step number two, when we are still holding the charging rod in place, we shall earth the metal sphere. We connect the earth into the metal sphere. When we do so, these negatives which had been repelled to one side, they will now flow to the earth. Electrons will flow to the earth. Here they are moving, going to the earth. That's leaving behind our positive charges. Please don't do this after taking away the inducing charge. We put the earthing wire where we are still holding our inducing charge in place. Then don't take away the inducing charge before you take away the earthing wire. Next, take away the earthing wire while you are still holding the inducing charge in place. If you take it away, then we shall be left with a body having only a positive charge. Now, when you later take away the inducing charge, the positive charges will redistribute themselves across the conductor, and you'll have a positively charged conductor or sphere, charging a body negatively by induction. If you want the body to be charged negatively, this time we use a positively charged rod. That is the principle. So we place our neutral conductor on an insulating stand. Then we bring the positively charged rod near the neutral conductor. What happens? It attracts all the negatives on one side near the rod. Then it will repel all the positives onto the far end. Step number 2. While you are still holding the inducing rod in place, we earth the metal sphere. When it is earthed now, because these positives which are repelled away are massive, they don't have to run to the earth. That is the principle for the positive. They don't move anyhow. So instead, the electrons will come from the earth and neutralize all the positives which were here. So we are left with a conductor with a negative charge only. But since we are still holding the inducing charge in place, these negatives are still in one place. Next, before you take away the inducing charge or the inducing rod, take away your earthing wire. When you take it away, and you later take away the inducing rod, the negative charge will distribute themselves equally across the conductor. Thus, we shall have a conductor which is negatively charged. Now we shall look at the method of charging bodies by separating them. Now, this time we want to charge two bodies differently by induction. What do? We get two conductors A and B that are neutral. We place them on insulating stands such that the two conductors are in contact or they touch one another. Step number 2, bring an inducing rod. This time you can bring any type. Bring an inducing rod. This time I have a positive rod near one end of the two conductors. When I bring it there, it will induce a positive charge on a negative charge on the near end and repels the positive charge on the far end of conductor B. So it has successfully separated the electrons and the positive charges on the two conductors. Since now they are behaving like one because they're in contact. While we are still holding the inducing charge in place, we separate these two metal spheres by means of their insulating stands. So they are now separated. When we later on take away the inducing charge, the negative charge will distribute itself on conductor A, while the positive charge will distribute itself on conductor B. Therefore, we would have charged the two bodies differently by induction. We're going to stop here with the first part of introduction to electrostatics, and we still have another part of this very episode so that we can digest these concepts one step at a time. Look out for the next part of this very episode of Introduction to Electrostatics.